Previous videos have developed the first and second law of thermodynamics and the relations that arise from them. These relations are based on the variables that govern the physical universe: mass, heat, pressure, volume, temperature. Maxwell's relations are a way to demonstrate how the first and second law relationships are intertwined, and also how they can apply to real-world situations with real gases. First of all, we'll start with the concept of fundamental equations, which are expressing thermodynamic functions in terms of the state variables, pressure, volume, temperature, and moles, where for now, once again, we can ignore moles because for a homogeneous system, that's simply a scalar. And the fifth variable is also left out because, as has been shown, heat is related to entropy, with the definition of entropy equal to dq over T. The thermodynamic functions are internal energy, enthalpy, Helmholtz energy, and the Gibbs free energy. From previous videos linked below, the Helmholtz energy is defined as minus the integral of entropy times the change in temperature minus the integral of pressure times the change in volume. Temperature and volume are two of your state variables, so the Helmholtz energy is already a fundamental equation related to temperature and volume. The Gibbs energy, also described as minus SdT plus VdP, is already a function in terms of state variables, temperature and pressure. So the Gibbs energy is a function of temperature and pressure. Internal energy is a function of heat and work. Those are not state variables. However, work is defined as the integral of PdV, where volume is a state variable. And since delta S is equal to the change in heat over the temperature, change in internal energy is T ds minus PdV as a fundamental equation. So the internal energy is a function of the state variables entropy and volume. The fourth, enthalpy, is the internal energy minus work, or dq minus PV plus the change in PV. Expanding this out, you get TdS minus PdV for delta U, and the total differential of pressure and volume is VdP plus PdV. The PdVs cancel, and you find out that enthalpy as a fundamental equation is equal to TdS plus VdP, where enthalpy is a function of entropy and pressure. These fundamental equations, first of all, go to why most chemistry students are familiar with H and G as letters of the alphabet, but not U or A. If you look at the Helmholtz energy and the internal energy, they are both functions of volume, while the Gibbs energy and the enthalpy are both functions of pressure. Chemical reactions usually occur by mixing two things together, so the volume never stays constant. Hence, the internal energy and the Helmholtz energy don't apply. However, these reactions are usually done in a room under atmospheric pressure, under a constant internal pressure. So chemists use enthalpy and the Gibbs free energy. Once you know the fundamental equations, you can develop Maxwell's relationships. You know Helmholtz energy is minus SdT minus PdV, internal energy, TDS minus PDV, enthalpy, TDS plus VDP, Gibbs energy minus SDT plus VDP. Maxwell's relationships come from taking a total differential. For example, the total differential of the Helmholtz energy would be the partial change of A with respect to T at a constant V, plus the partial of A with respect to V at a constant T. I look at the partial of A with respect to T at a constant V, and I find out the only thing that remains is minus S. So the partial of A with respect to T at a constant V is minus the entropy. I look at the partial of A with respect to V at a constant T, and the only thing that's left is minus P. So the first two Maxwell's relationships are the partial of A with respect to T at a constant V is minus S. Partial of A with respect to V at a constant T is minus P. Internal energy, the total differential, would be the partial of U with respect to S at a constant V, which is going to be equal to, once again, you get rid of the U, you get rid of the S, you get rid of the V, that's equal to temperature, plus the partial of U with respect to V at a constant S, where the only thing that remains is, again, negative P. Enthalpy. The partial of H with respect to S at a constant pressure leaves you with temperature. The partial of H with respect to pressure at a constant entropy leaves you with volume. Gibbs energy. The partial of G with respect to T at a constant P leaves you with minus S as the result. The partial of G with respect to P at a constant T leaves you once again with volume as the result. Maxwell's relations are based on differential equations, which most people just don't flat out enjoy. Max Born, a very famous chemist, did not enjoy it either, so he came up with a graphical system. He made a box. He had, in a diamond, your thermodynamic functions, A, U, G, and H, and flanked each with their natural variables. So the first line, A is a function of V and T. H, G is a function of T and P. H is a function of S and P, and U is a function of S and V. You can use this mnemonic to graphically come up with the Maxwell's relations. For example, if I want to find the partial of A with respect to T at a constant V, I wind up going down from V to get entropy. So I get minus S. The partial of H with respect to S at a constant P goes up, so I get T. If you go down, the sign is negative. If you go up, the sign is going to be positive. This mnemonic works like a game of Sudoku. If I'm going to find T, T is opposite of S and is a variable of both U and H. So, the partial of H with respect to S at a constant P gets me to T, or the partial of U with respect to Vs at a constant V also gets me to T. If I want to find volume, volume is diagonally across from pressure. Pressure is a natural variable of both enthalpy and the Gibbs free energy. So the partial of H with respect to P at a constant S is volume, or the partial of G with respect to P at a constant T is also going to be volume. If I wish to find entropy, entropy is diagonally across from temperature. Temperature is a natural variable of the Helmholtz energy and the Gibbs free energy. So the partial of G with respect to T at a constant P, this time I'm going down, so it's going to be negative, is going to be equal to the partial of A with respect to T at a constant V. Both of those would be equal to negative entropy, or entropy would be equal to negative of those differentials. P is diagonally across from V, which is a natural variable of the internal energy and the Helmholtz energy. Since I'm going down, I get a negative sign. So the partial of U with respect to V at a constant S is negative P, or the partial of A with respect to V at a constant T would also be negative P. In this case, as I'm going from bottom to top, as I am going looking for the variables on the top, temperature and volume, I'm going up from my differential, so the sign is positive. If I am looking for enthalpy or pressure, my differentials are going down, so the sign is going to be negative. This also works. So if I go from left to right, if I'm above the line left to right, the answer is positive. If I'm below the line left to right, the result is going to be negative. This also works going around corners. If I want to find the partial of S with respect to V at a constant T, that's going to be equal to the partial of P with respect to T at a constant V. If I want to find the partial of V with respect to S at a constant P going around the corner, that's going to be the same as the partial of T with respect to P at a constant S. Since the arrows point to each other, these two are equal. If I go left to right, the arrows point to each other, the differentials are equal. However, T with respect to V at a constant S versus P with respect to S at a constant V, instead of going up and down, or left to right rather, I'm now going up and down, the sign's going to be negative. Similarly, the other corner, S with respect to P at a constant T, is going to be equal to, but opposite of, V with respect to T at a constant P. So once again, if I'm taking the corner going from left to right, the sign is positive. If I'm taking it up to down, the relationship is negative. So here are all of Maxwell's relations between state functions to actually find state variables. Temperature is the partial of H with respect to S at a constant P, or U with respect to S at a constant V. Volume is the partial of H with respect to P at a constant S. or G with respect to P at a constant T. Entropy is minus G with respect to T at a constant P, or minus A with respect to T at a constant V. Pressure is minus U with respect to V at a constant S, or minus A with respect to V at a constant T. Between the state variables, entropy with respect to volume is equal to pressure with respect to temperature at a constant V. Volume with respect to entropy at a constant P is equal to T with respect to P at a constant S. T with respect to V at a constant S is minus P with respect to S at a constant V. S with respect to P at a constant T is equal to minus V with respect to T at a constant P. You'll see in a moment that these relationships are very useful for using thermodynamics in real-world situations. They're also not intuitively easy to remember, which is why the mnemonic of VAT, SHP in the box is actually so useful to get familiar with because it comes in handy when you need it. When would you need it? Let's do a comparison. I have a perfect gas for an isothermal process. Delta U is dQ minus PdV. Delta H is dQ plus VdP. Since PV equals nRT, for an isothermal process, if the temperature is constant, pressure and volume have to stay constant. So you get the well-known and established isothermally, delta U is CVdT equals 0. Delta H is CPdT equals 0. For a real gas, delta U as a state function is defined as TdS minus PdV, or the partial of U with respect to T at a constant V, dt, plus U with respect to V at a constant T, dV. The definition: the change of internal energy with respect to temperature. If I keep volume constant, PdV is 0, that is the definition of the heat capacity at a constant volume. So the internal energy from the fundamental equations is also, dQ is also TdS. So I can write this as U with respect to S at a constant V minus U with respect to V at a constant S. Maxwell's relations let you do a couple of things that do not at present seem quite intuitive. The change of U with respect to V at a constant T would therefore be T times S with respect to V at a constant T minus P by simply dividing TdS minus PdV divided by dV. This does not equal 0. Even though the partial of U, the change of U at a constant temperature should be 0. But with respect to the volume, it does not wind up being 0. I wind up with this term, the partial of U with respect to V at a constant T, T times dP dt minus P, has terms in it. It winds up being something called alpha T minus kappa P over K, where for a real gas, this is called the internal pressure of the gas. Theoretically, an ideal gas has no volume. The gas should be able to be compressed to zero. However, a real gas cannot be infinitely compressed. There is an internal pressure that keeps it alive. In this, alpha is something called the cubic expansion coefficient. Kappa is known as the isothermal compressibility of the system. So I keep looking at real gases. Enthalpy. TdS plus VdP. Partial of H with respect to T at a constant P dt plus the partial of H with respect to P at a constant T dP. H with respect to T is the definition of the heat capacity. dH is also equal to H with respect to S at a constant PdS, H with respect to P at a constant TdP. So H at a constant with respect to T at a constant P is equal to H with respect to S at a constant P ds. If the enthalpy is zero for an isothermal system, the change of heat of enthalpy with respect to T at a constant P is going to be minus the change of enthalpy with respect to P at a constant T. This is probably getting a bit hectic. I can find delta T and I can find delta P in terms of differentials. Delta T is minus the change in H with respect to P at a constant T. Delta P is delta H with respect to T at a constant P. That equals to, so the change in temperature with the change in pressure is equal to the change in temperature with respect to pressure at a constant H. This is called the Joule-Thomson coefficient. Again, Maxwell's relationships in real gases are mathematically difficult and probably not that interesting, although you will seem to, in a couple of seconds, you'll find out that you really do enjoy this fact that the partial of T with respect to P at a constant H is equal to this Joule-Thomson coefficient. So let's suppose I build a system. Around a compressor attached to a thin pipe that expands to a thicker pipe. I then start circulating gas through the system. Where the thin pipe produces a high pressure, the thicker pipe produces a low pressure. For an ideal gas, the change in temperature with the change in pressure, if enthalpy is zero, is going to be zero. However, for a real gas, the change in temperature with respect to pressure at a constant enthalpy is the Joule-Thomson coefficient, which is positive. So what you have now invented, as the pressure decreases, the temperature decreases, which essentially means one has now invented air conditioning. Air conditioning works by expanding a gas from a narrow tube into a wider tube at a constant enthalpy. For an ideal gas, that expansion would not change the temperature. However, for a real gas, the temperature decreases So this is how air conditioning works, and it would not work if the world consisted only of ideal gases. So that's it on Maxwell's relationship and on the fundamental bases of the first and second laws of thermodynamics. The next set of videos will examine what happens if one deals with the variable that's been ignored. What if the number of moles change? I hope you're enjoying this or finding it useful.